Okay, we'll look at some exponents. Okay, exponent like 2 squared is 2 into 2. 3 cube is 3 into 3 into 3. Okay, these are different exponents and we are raising it. So similarly, there is one exponent called e, okay, which is very special. Okay, if you will see it everywhere. Okay, the exponential decay, exponential rise in population, exponential component. If you look at the equation of the normal distribution, you will have like e to the power minus x minus mu by sigma something. So e is one of the exponent which is very special compared to other exponents. We'll understand the connection between the exponents and logarithms and how why this is special. Okay, now e is also known as 2.718. It's a constant. Okay, like we have 2, e represents this number 2.7. Why is it so? I'll see that. So let's take this example of 2 to the power of x. We are trying to raise the exponent of this, and we wanted to say we wanted to double double the double the money we invested in. So it means that we are raising it to the power of 2. Okay, we want to double the money. If you wanted to raise when population is getting doubled, this becomes the base. Okay, so we start with 2 and it becomes double. It becomes 4. Then the double of 4 becomes 8. Okay, so 2 to 4. Okay, then and 4. 2 to 4. 4 to 8. Okay, then 4 and 8. Okay, 8 doubles and becomes 16. Okay, so basically we are kind of doubling because that's what the exponential means. So if you apply the concept of derivative and try to find out what is the change if what is the rate at which this doubling happens if you make a small change. Okay, and if you try to find the derivative of this. Okay, let's say we wanted to find the derivative of this function. So I'm making a small change to x. Okay, that is x plus dx, and I wanted to find what is the corresponding change. Okay, I'm making this is like dx. I'm making a small change in x. I wanted to find out the proportion by which this doubling happens. Okay, and this is what it means. So in exponents, what you can do is if you're having let's say 2 to the power of 3 plus 2, it is equivalent to saying 2 to the power of 3 into 2 to the power of 2. Same way. Okay, you can write 2 to the power of 3 and 2 to the power of 2 as you can add these two and make it like 2 to the power of 5. Okay, this is how exponent works. So similarly, if you apply this here, it will become 2 to the power of x in the numerator into 2 to the power of dx divided by dx. Okay, that is what this means. Now, what this means is the 2 to the power of x is kind of a factor, can factor out, and it changes like this. So which means you start with 2 to the power of x and you also have the 2 to the power of x, which means this forms the base and some proportionality constant is what this gets multiplied with. Okay, so we're trying to find out what this value could be. Okay, the small change in dx, so which happens to this function, and you kind of get the original function back and the corresponding small derivative. Okay, if you multiply these two, you will probably get to know what is the change in the rate in which this changes. Now let's take this to very small numbers, like let's say 2 to the power of x into, let's take dx as a very small number. Let's say okay, and I wanted to also subtract the original 2 to the power of x here, because we're taking the difference between the change in x with the original minus x. So this will all be together. This will all continue. We have to subtract it. Okay, so if you factor this, there's a small change here, and 2 to the power of x will become 2 to the power of dx minus 1 divided by dx. Okay, and now this 2 to the power of dx will be can be factored out, and it becomes 2 to the power of dx minus 1 divided by dx. Now let's apply a very small value of this dx. So this becomes 2 to the power x into, let's say the number is 2 to the power of 0.0001, okay, minus 1 divided by 0.0001. This is, let's assume that the dx is a very small number, and you get a constant like this 2 to the power of x into 0.69 something. So this proportionality constant is what this is what, if you multiply with this, is the rate at which this changes. Okay, so every exponent will have a proportionality constant. Okay, you start with, let's say, if it is 3 to the power of x, okay, and it will end up like 3 to the power of x into some proportionality constant. Okay, it could be like some number like 0.27 or something. It could be any number, but it is a constant. Okay, so this is how the proportionality constant is applied to the base, and we can find the rate at which in doubles. This is to find out the rate at which everything triples, and if you put 4 to the power of x, it is like rate at everything quadruples. Okay, this is how the exponential changes can be visualized using small incremental changes multiplied by the proportionality constant. Okay, and now if you try to find out the proportionality constant of E, okay, like we have this, okay, that is the 2.71. If you use 2.718 as the number, and if you try to do a proportionality constant and try to derive the same thing, this constant becomes e to the power of x into 1. So what it means is that E is a number which kind of exponentially increases with the proportionality constant of 1. Okay, if it is 3, it will have a different number. If it is 4, it will have a different number. And even though everything has the base of starts with, the base is 2 to the power of x or 3 to the power of x or e to the power of x, E alone is a proportionality constant of 1. So which means that the rate by which e to the power of x changes is by itself. Okay, it is, if you multiply it by 1, it is the rate at which it changes by itself, and we don't have anything which is like in decimals, or if it is like like 4 to the power of x, it would be some number greater than 1. So this constant 1 makes this unique. So what this really means? Okay, what do you mean by a constant change? So for any function, let's say let's take this function e to the power of x, and let's say this is e to the power of x. Okay, and the derivative of this function is the value as the function at this point. So which means that if you want to find the derivative of e to the power of x, we have like derivative of the function e to the power of x dx is equal to e to the power of x. The derivative is itself. So what it really means is that at any point in this function, the derivative of this function is the point at which the point itself. So derivative at this point is this point. Derivative at this point is this point. And the area under the curve at this point is the derivative. So this is the only function which has this property. That is the reason E is special. So that's the reason the proportionality constant is 1. Suppose if you have a function called x squared, okay, a different function. It's not exponential function of x squared. The derivative is 2x. Okay, it kind of changes the format. Okay, x squared becomes 2x. In this case of E alone, the derivative of it is itself. Okay, here the derivative of x squared is not itself, it is something different. So only for this function, the derivative is itself. And what it really means is, again, derivative at this point is the value of the function at this point. Derivative at this point is the value of the function at this point. So that's the constant derivative. And if you want to find the area under the curve at this point, is the derivative, is the same value at this actually. So this is very unique about E. Okay, now we are talking about the constant 2.71 and things like that. So what it really means? Okay, what the 2.71 is really means. We'll take another example of how this constant was arrived, and we will see how it all relates. Let's take an bank interest example. Okay, that's where this number first was noticed. Okay, and that's where they identified this constant. So let's take we wanted to kind of increase our investment in the bank by using the interest they gave, and I mean the bank gives to us. Okay, we wanted to increase the value of the money by using the interest, compound interest. So what is the value? I mean, like, let's say you have 100 rupees or $100 you have invested. Okay, at the end of the year, if the bank gives let's say 10% interest, you will have 110 rupees. Okay, or you can $110. Okay, whatever it means. So basically, if the bank gives 10% interest at the end of the year, you will have 110 rupees. That is like the principal is 100, the rate of interest is 10 percentage. Okay, and the number of period of, I mean, like, number of years is 1. Okay, the period is 1. So if you look into the total amount you will get, it is like this. You can given P into 1 plus R by n the whole power R t. Okay, this is the formula of finding the compound interest. So your principal is 100, and this is the rate of interest. Rate of interest is 10 percentage. Okay, let's it's like 0.1. 10 by 100 is 10 percentage. Yeah, it is 0.01. Okay, number of years is 1. Okay, and the rate of interest is 0.01 into t is 1, so 0.01. So this is what is your sorry, this is what is your formula nt, the number of time periods. It's 1 year. Okay, this is how you calculate the rate of interest. So this is the same thing. This becomes 100 100 plus 100 into 0.01, 100 plus 10 becomes 110. So if you want to double, I mean, if you have the bank, I mean, the bank gives you interest at 10 percentage. Okay, and if you are able to wait for 1 year, you get 110. Okay, that's how the interest works. Now, instead of let's say the bank gives you 100% interest. Okay, instead of 10% interest, it gives 100% interest. No bank is going to give you, but it's assumed that it's 100% interest. So what this becomes is, this becomes 100%. This becomes 1. So this becomes 100 plus 100, and your money becomes 200. Okay, which means your money is getting doubled at the end of the year. So if the bank is giving 100% interest, you get 100. I mean, like, you double your money. So now there was a curious case where they wanted to find out if instead of giving the interest once in a year, if I give it twice in a year, okay, probably I might double the money faster. Right? Definitely, if this rate of interest becomes the number of time periods becomes 0.5, you might, instead of waiting for one whole year, I mean, you might double the money in half of the year. So what if the interest, I mean, like, what if you try to give the interest, let's say quarterly, 4 times a year, then 5 times a year, okay, 6 times a year, and if you start increasing, trying to find out, if you increase the period of by which you pay the interest, okay, am I going to double the money and make infinite amount of money, is what the intuition says, right? If the interest rate calculates. So what happens is, even though the rate of interest, I mean, you double the money, and that's what this 2 means actually. The constant E, 2.718 is what it means. You double the money plus you make some additional money, and irrespective of number of times you calculate the interest, okay, instead of yearly you started with, you doubled at the end of the year, you made it half yearly, you doubled at the half of the year, and if you made it quarterly, you doubled even earlier. So even if you try to make it like monthly, daily, and within 24 hours, you split it into like every 6 hours and every second, okay, whatever you do, the maximum value you can double your money is about 2.718. This is the ratio by which you can double. You cannot make infinite amount of money. It reaches this constant actually. Okay, so that is how they identify this value of E through this bank interest example. You cannot infinitely, even though if you try to compound the interest at infinite time intervals, okay, rather than yearly, monthly, and if you do it every second, if the bank tries to give you interest every second, this is the maximum you can get. Okay, your 1 rupee can only become 2.718. It cannot go beyond that, irrespective of whatever it is. So I just took 100 rupees as an example. This E is nothing but if you have invested 1 rupee and try to double your money with infinite interest. I mean, interest is calculated at infinite time intervals. You will sorry, infinitely small time intervals. You will get this. This is the amount of money you will get. That is how this E is arrived. Okay, now this E is what you see it in the exponents. This is what you see it in as the derivative has got its own constant. E to the power of x is equal to derivative of e to the power of x dx is equal to itself. Okay, so this proportionality constant is what makes E so special. Okay, it's derivative of itself. Okay, this is a brief history of E. Now we can extend this idea of E and other stuff using infinite series. Okay, what you call as an infinite series. Infinite series is nothing but trying to add some things infinitely. Suppose let's take an example. Okay, you start here. Okay, you start here at the point A, and you wanted to reach point B. Okay, there is a rule which is given to you. Like two of you start here. Okay, two of us start here from point A to B. The rule is you can take half of the distance as one step. Let's suppose we assume that we have very long legs. The first step you can take half of the distance. You are dividing it by 1 by 2. Okay, this is the first step. This is the total distance is 1. You can take half of the entire distance remaining as the first step. Now, a second step, you should still follow the same rule. You should take only half of the remaining distance. So probably you will come here, okay, like this point. So now again you will have to take half of this remaining distance. Now again you will have to take half of the remaining distance. So you are trying to reach the destination, but you are allowed to take only maximum half of the remaining distance. So if you try to keep halving things, okay, you will start from say 0, let's say this is 1, okay, here you have reached 0.5, then here you might have reached 0.75, and excuse me, here you might reach 0.9, okay, and you will infinitely be chopping this distance remaining into half of it, and you will never reach 1, but you will keep moving like 0.9, 0.991, 0.992. You will still be close to 1, but you will never be 1. Okay, this is what we call it as an infinite series. You will approximate to some precision, but you will not reach it. So if you are in solving a problem through calculus, okay, you should say that okay, I have reached 0.99999 one of my destination, which is equivalent to 1. I can move on. It's solve the problem and move on. If you are like if you want an analytic solution and try to find out, no, I haven't reached 1, I will still try, and you will probably have to wait for infinite calculations to happen, and the series will never end because you are trying to halve the distance every time, and you will never reach it. Okay, so this kind of adding things infinitely is what is called as an infinite series actually. Okay, this is an intuition of how you remember an infinite series. So there is a relationship between your trigonometric function and infinite series. So let's say you have a cos wave, okay, something like this. Okay, it's a cosine wave. So as we all know, cosine cos 0 is this is cos 0. Okay, at 0 this is 1. Okay, and this is 1. Okay, so this is like cos 0. This is cos 0. 0 degree is 1. Okay, so this is a cosine wave, and this can be written as cos theta. Okay, the cos theta, this wave. Now, this wave can be represented using infinite series, using components of numbers which can be added together. Okay, so let's say you want, this is the wave. Okay, this is the wave you wanted to work with. But sometimes these waves are difficult to, I mean, if the waves are like kind of getting complex to take the derivatives and work with, we can try to approximate this wave into a smaller, into a different form, which can still be a very good approximation for this wave, and we can still work with it. So let's take that we want to approximate this portion of this wave. Okay, this is the cosine wave. Okay, and let's say we are trying to approximate this wave like this. Okay, so this is not a cosine wave, but for majority of the cases, let's try to keep it as close as possible. So this is a different wave, different equation. But if you see this portion, you can whatever you want you are trying to do with cos x, you can try to do with this this graph as well. Okay, because it also peaks at it is also having value of 1 at value of 1 and x is equal to 0, and it is also following same pattern of slope close to each other. It's not exactly the same, but close to each other. So when you try to approximate this kind of wave functions using a polynomial function, this is what they call it as Taylor series. So here in this is a trigonometry function. This is a polynomial function. So this polynomial function could be like 1 plus 1 minus x squared by 1 factorial or something. Okay, if you're trying to this is a trigonometry function, okay, and this is a polynomial function. Okay, both are different families of functions, but we are trying to approximate this using this. Okay, and this can be used to solve some of the problems. So in this case, it is like 1 minus x squared by 2 factorial. Now this doesn't stop here. Okay, this cos theta can be it keeps moving like this. Okay, plus x to the power of 4 by 4 factorial, then minus x to the power of 6 by 6 factorial. So basically, we are trying to add terms infinitely small. Okay, and try to build this graph as close to this original graph as possible. Okay, but as you add more terms, certain things you might not need beyond certain point of point of precision. You can ignore the terms. Okay, in this example, if I say cos 0.1, okay, if you put it in a calculator, let's say it gives you 0.995 or something. Let's say it gives you 0.995 something. If you just use this 1 minus x squared, like 1 minus 0.1 the whole square by 2 factorial, we might still get 0.994 or something. So it's still see, if it's just two terms, okay, you are ignoring 4 factorial, so it keeps continuing, it's an infinite series. Okay, you can still approximate this the value of 0.1 using this polynomial function, and this is what this is what's the connection between your trigonometry functions and the polynomial functions, and how we can approximate using infinite series to get this get the same exact value of let's say cos 0.1 to arbitrary precision. Okay, it will not be exactly the same, but it will be close enough to such a way that it's enough for us to work with. So why do we do this? Why do we try to understand infinite series and things like that? This will help us to understand what we call it as a Taylor series, and it helps us to approximate some complex equations. So suppose if we have a machine learning algorithm which is having a complex cost function, you can approximate that using a Taylor series, using the first few terms, and ignore the lot of computations which may not be worth pursuing if you're able to get some precisions close to what you need. Okay, this is how we kind of use the relationship between the trigonometric functions, exponents, logarithms, and your infinite series. Okay, now we will expand this idea a little bit more. Okay, now I mentioned about the cos theta. Okay, this is what the cos theta is all about. Now let's take one more example of e. Okay, we started with 2.718, right? Now e to the power of 1, okay, we can be written as 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial and things like that. So if you just calculate this, it becomes 1, then 1 plus 1 by 1 factorial is 1, okay, then 1 by 2 factorial is 0.5, and 1 by 3 factorial is this is like basically 1 by 2, this is like 1 by 6. 1 by 6 becomes 0.16 or something. So if you try to add this, like 1 plus 1, 2, 2 plus 0.5, 2.5, 2.5 plus 1.6, 2.616 or something. 2.5, 2.66 or something. So if you see, we have, this infinitely this infinite series, okay, which you can keep moving, okay, so that's 1 by 1 4 factorial plus 1 by 5 factorial and so on, okay, and it's going to give you the number 2.718, okay, if you keep infinitely doing it, and we're almost getting it at the third point, okay, with third factorial we're almost reaching 2.77. Suppose if you add 1 by 4 factorial, probably you'll end up like approximately like 2.7 something, 2.7 something. So just add one more factorial for 4 factorial, you'll get 2.7 something. So with just 4 factorials we're able to approximate infinitely long series with just 4. This is called a Taylor's approximation. You can use this just 4 terms to approximate this number. That's what I was trying to explain using the earlier example of cosine as well. Okay, so you can use this. So this is what you call it as approximation. So now let's connect all the things together, because we have one equation in mathematics which is called e to the power of pi I is equal plus 1 is equal to 0. Okay, something which is a very famous equation. We'll try to connect this whatever we have learned so far using this infinite series, and try to see if we can get to this. So this is the series of E. Now I already gave you an example of cosine. Okay, cos x, that is nothing but your 1 minus x squared by 2 factorial plus x to the power of 4 by 4 factorial and things like that. Okay, minus the sign keeps changing, minus x to the power of 6 by 6 factorial. So similarly for sine, it starts with I think x plus x by this is even, this is odd, I think, x by x3 by 3 factorial, I think plus x to the power of 5 by 5 factorial and x to the power of 6 5 6 7 by 7 factorial and so on. So, and here I think this sign changes, okay, minus plus minus. So if you see, there is some pattern in this, okay, there is in here, I mean here it is like e to the power of 1 is 1 by 1 factorial, 2 by, 1 by 2 factorial, 1 by 3 factorial and so on. Here it is having x, which is like x cube by 3 factorial, x to the 5 factorial. There is a here everything is positive. Here the signs are changing, okay, between negative and positive. If you try to add these two, probably if you try to get, I mean, if you think that you might get this, probably the sign might be a problem. Okay, so instead of e to the power of 1, I mean like 1, probably we can try to put e to the power of okay, because we wanted to make the sign in such a way that if you try to add these two, it becomes I mean if you try to express e as the sum of this cos and sin x, if you're able to get if you're able, sorry, excuse me, if you're able to get this, that will be great, but we are trying to get there actually. Okay, so let's see if I mean there is, if you wanted to make a negative number positive, okay, or if you wanted to deal with negative numbers, I think if you remember in the numbers session, we just talked about how I squared is equal to minus 1. Okay, so if you're able to replace this minus 1 with I, okay, and probably that might help us to solve this problem, because we can try to make this positive by using I squared. Okay, this is I. Okay, so let's see if we can do something with that. Let's say instead of x, if we try to put pi in I, if you try to put I, okay, let's see what happens. Let me check that. We'll continue. We'll try to, instead of using e to the power of 1, we will try to use e to the power of ix. We're just replacing this 1 with ix. So this becomes 1 plus ix by 1 factorial. This becomes ix squared by 2 factorial. Okay, actually this is like 1 squared to the cube to the 4 and to the 5. It should exponentially increase actually. Okay, I squared by 2 factorial and ix cube by 3 factorial and so on. Okay, so we are trying to increase, replace this 1 with ix, trying to see what happens. Now if you see here, this equation becomes 1 plus ix, okay, ix by 1 factorial, and this here it becomes minus, I squared becomes minus 1, so it becomes minus x squared by 2 factorial, and here it becomes I squared becomes minus 1 and there is one I, so it will become minus I x by 3 factorial. Okay, and then it will keep continuing. Okay, if you see here, it has got the term I, it has got the term okay, it has got certain terms are with I, certain terms are not with I. If we try to group things together, what will happen is you will get something like this, which is equal to 1 minus x squared by 2 factorial. We will try to group this, and we will take I, which is common, okay, plus I, and you can say x by 1 factorial and minus x cube by 3 factorial and so on. Okay, so there is a component with I and there is a component without I, and if you see the corresponding cos equations, so this is nothing but your cos theta, this becomes plus I into this becomes your sin theta. Okay, x minus x cube by 3 factorial, x to the 5 factorial, so this becomes your sin theta. Okay, now instead of e to the power of ix is equal to cos theta plus I sin theta. Okay, that's the equation we have received. So instead of just using I mean at x is equal to pi, let's take this, instead of x we use pi, e to the power of I pi or pi I. Okay, this becomes cos this x is x actually, cos x plus I sin x. Okay, cos becomes cos pi plus I sin pi at cos pi. Okay, so if you remember what is cos 180, cos 180 is let's draw it actually. This is a cos graph. Okay, it starts here, it goes like this, or you can draw it like this. Okay. Cos 0 is 1, cos 90 is 0, cos 180 is minus 1. So this becomes minus 1. E to the power of I pi is equal to minus 1. And sine at pi. Okay, sine is what this is the sine. Sine at 0 is equal to this is cos 0, which is 1. And this is sine at 0 is equal to 0. Sine this one. So sine 180 is basically 0. Okay, so which means that e to the power of I pi plus 1 is equal to 0. This is what this equation is. So cos 180 is minus 1, sine 180 is 0. Okay, and if you try to find this equation, this is what this equation is. So this is one of the very famous equations. So we have tried to connect the dots between logarithms, exponents, infinite series, and how this all connects to solve some of the complex equations and mathematics using some approximations. Okay, thank you.